All right, welcome back to Engineering 255. This is the third video of chapter 7. In this video, we're going to introduce an idea called the shear and moment diagram. To find this diagram, you have to find the equation to represent the diagram. So we will go through some of the example and give you an idea and show you some step-by-step process to create these kind of diagrams. So right now, if you look on the screen, what we wanted to do is to plot a shear diagram. The shear diagram is the shear force versus the x, where the x represent the position of the member. And the moment diagram is the same, is going to be the bending moment versus the x. If you want to calculate value, if you know the function, so what we were trying to do is that we need to derive this equation. This equation meaning that the shear force depends on the x. Same thing for the bending moment. The bending moment depends on the x. So at a different location, you will have different moment. You will have different shear force. We can find a function, or you can make a drawing to show how they are related. In the picture that you see it here, let's start with the picture of A. So the picture of A represents a situation. You have a member, which is this one here, a beam. At the point of A, you have a pin. At point of B, you have a rotor. So, and near the pin position, you have this kind of a load, which is a distributed load. At the same time, we have a concentrated load at the position of B, and that is P. So this W represents the load per meter, okay? And this could be any of the function. It doesn't have to be uniform distributed. It could be a triangle, like the triangle that we use a lot. It could be some other function as well. If I have this loading situation, I wanted to know how the shear force varied at the location. By looking at different position, I wanted to know what is the value of the shear force. We can also find out what is the value of the bending moment as well. So if you can plot this graph and this graph, then I can clearly use the drawing to identify what are the value at the different position. So this one is called a shear diagram. And this is the bending moment diagram. Or sometimes we just call moment. What we really care is that if you have this diagram, I can clearly identify where is the most loading that will apply to this member. Let's say, for example, if you look at the shear force diagram, you can see this is the maximum value. This is the minimum value. So the maximum value tells me how much load the member has to support. So when you design this member, you will select the property, the material that can support this kind of load. Bending moment is the same. So the bending moment, you can see clearly the peak is happening at the point of B. This point of B is actually where this one is applied. So at that point, you're going to suffer the most bending moment when you design the object. You have to be careful at that point. That would be the critical point that you wanted to focus on. So all this section is going to focus on that. Let's see the example how we work on this. So here is an example. We have a setting figure 7-11, and it's a very simple member like a shaft, and it's supported by both ends. The point A and point C, these two are like a bearing. So the bearing simply has some like a circular item inside of the housing, and the shaft just go through this and supported by two ends. It allows the shaft to rotate, but it doesn't allow the shaft to move up and down or left and right. So this is what that situation is. At the same time, we apply load at point B. Where the point B, you have 5,000 Newton load applied to that position, which is happen to be the middle position of this bar here. Okay, so how do we solve it? How do we make a shear force diagram and bending moment diagram? The first step normally is that you have to start by using the entire structure free body diagram to find the support reactions. The support that we have is at point A and point C. So in this case, you could have the X direction and also have the Y direction. Because there's no loading actually in the X direction, so we don't really need to care about if you have this kind of a bearing. Actually, it's simply just supported in the Y direction, so it doesn't allow it to move up and down. So we have Y direction at AY and at a CY. And you have a force going down, which is 5,000 Newton. And to solve this problem, we can use the summation of F of Y equal to 0, which is equal to AY plus CY. That has to be equal to or minus 5,000 equal to 0. So that means the AY plus CY has to be equal to 5,000. That's easy. But if you want to solve these two, you need additional equation. The other equation that we use is the summation moment. So we can use the summation moment at A. If you do summation moment of the A, and there's two forces will contribute the moment, which is this one and this one here. So 5,000 K will make this one rotate clockwise. So we're going to make this one to be positive counterclockwise. So this will be minus 5,000 and multiply with the distance, which is 2. For the CY is going to be positive, and that will be CY multiplied with 4 meters. And that will be equal to 0. So then you can solve for the CY, and CY is going to be actually 2.5 K, which is 25,000 Newton. And therefore, your AY is going to be 25,000 Newton as well. So now we solve this one, and we will show you why these two are important. Because when you have a value, an n value at some position, that will make changes in your diagram. That means at that point, you're going to suddenly change the value of the shear force, and you will probably change how the bending moment looks like as well. Now, the second step after you finish this is that we're going to cut the beam into a smaller section. And then we're going to draw the free body diagram, and we're going to determine what is the N and the V at that cutting point. So if we start from the point of A, okay, and we're going to slowly go to the right. And if you don't see any changes, you can either cut it at here or cut it at here or cut it at here. As long as there's nothing change, then most of the time it will not change because this problem is going to be the same. So we draw a free body diagram between A and B. They just say we are drawing this just right before the B. So this is going to be the position of A. And here is the position of B, but we are drawing that just right before the B. Just right before the B, there's a 2 meter at here, but let's just say, well, I'm not going to make it a fixed number. I just know this is some X at here, but this X is going to be less than 2 meter. It's going to be greater or equal to 0 meter. We do have an AY here, which is 2500 Newton. And then we're going to draw the reaction when you cut it. And we have 3 different kind of internal loading. That's what we're trying to find. Because we're looking on the left-hand side, so this is going to be our V. We're not going to have an N, so I'm not going to draw the N, which is the actual loading. We also going to have a moment. The moment has to be positive if it make it bend upwards. So this is my N. So how do we find the V? If you look at this diagram, we simply just use the same summation f y equal to 0, and we have 2500 and minus v, that is equal to 0. So my v is simply just 2500 Newton. Now it doesn't matter what x that is, as long as the x is between 0 and 2 meters, this v is going to be the same value. You can assume x is 1 meter, then your v will be 2500. You can assume x is 1.5 meter, it's going to be the same. If we look at the summation moment, and we look at the summation moment at A, and we're going to make this one to be equal to 0. And the 2500 is not going to create any of the moment at point A because it's right at the point. The only possible moment that can be applied to that point is going to be the V and N that we have on the right-hand side. And let's just assume the same direction as my blue color one. So that moment is going to be in this direction to be positive. And we have the N itself. We also have this V here is going to create a moment, but it's going to be opposite to that direction. So I'm going to minus this one here. And V, but that is the force we had to multiply with the lever on. And the lever on is this one here, is the distance, which is a variable. It depends on how long this x is. This has to be equal to 0. So now we have moment, which is a function of x, and that's equal to v times x. And what is x? What is v? V is 25,000. Okay. All right. So that is what you need to do once you start to find out the supporting force. You cut the section into small pieces. Now, this is for the situation when you are looking from A to B, just right before the B, because when you are hitting to the position of B, the situation has been changed. So if we cut this member at another position, which is right after the B, then we can redraw this picture to a new diagram. Let me draw it here. So if we just go over to the B, where this is the B, and here we have a force which is 5,000 Newton. And we still have the A with 2,500 Newton. And that is the loading that you have. This is the point A. We do need to draw the reaction force. So still on this side, the V should be at this position. And the moment has to make it go upwards. So this will be our moment direction. You can do the same thing. We're going to do summation f of y equal to 0. So you have 2,500 is going up, minus 5,000 going down, and minus v, that equal to 0. Okay, so this is the situation when the x is less than 4 meter, but is greater than 2 meter. So my v is going to be equal to negative 2,500 Newton. We also can do the summation moment, and we can do summation moment at point A or point B. Let's do a point of A again, so that will be equal to 0. And the force will create the moment is going to be this one here. So we have, and then let's make this one to be positive. And then we're going to have, let me just move down to here. Okay, I'm going to use the picture to explain that. So I'm going to use this picture to explain what we were doing. This is a situation that we look at the section over the B, right? Same thing that we draw at here. And we need to mark the distance because this distance will tell us how much moment the lever arm is. And we're looking at this section here. So how do we calculate the moment? We have 5,000. If this is the positive direction, this one and it's going to make it go the negative direction. So negative 5,000 multiplied with 2 meter. And this V here is going to also make it go to the clockwise direction, which is negative V, and multiply with what? Multiply with this and this. You're going to sum these together. That is going to be the X. And also you need to modify, you have to add the moment at here, which is the moment that you try to find. You make it equal to 0. Your moment, which is function of the X, is equal to the V times X. The V times X and plus 100,000 Newton meter. Now, what is V? Well, V is this one here. So we're gonna put a V value at here. So that would be that will be this. This will be our M. Now, the next step is, if you look at this one, we are looking at the two sections already. At the end of this one, you're going to move to the point of C, and you will see what happened after we reach to the point of C. So now let me just summarize at here. When we are in this region, and we just did it, in that region, we have V is going to be equal to this, M is going to be equal to this. So Vx is going to be 2,500 Newton. This is a constant. The N is going to be equal to 2,500 of X, depends on the X. And when you are in this region, and we have Vx is equal to minus 2,500 Newton, And our m of x is going to be equal to 10,000 minus 2,500 times x. All right, so now you can draw the diagram. So if you have this function, that simply tell you this is a constant, right? So if we draw this diagram, which is the diagram of the v versus of the x, and we look at the two different regions from 0 to 2 meter and 2 meter to 4 meter. Between 0 to 2 meter, the value of v is a constant. So it's 2.5 thousand, and that's our v. And this is a positive value because this is a positive value. And when you are over the 2 meter to 4 meter, the value becomes negative 2,500. So the V becomes negative 2.5 K. And that's between 2 and 4. So this value is supposed to go to here. However, at the point of C, you have a change of the force because you push up 2.5 K Newton. So you can see initially was negative 2.5, but at the end we push it up 2.5 thousand. So this will goes to 0, which makes sense if you go over to the point of C, there's nothing in the member. It's supposed to be 0. There shouldn't be any of the shear force because there's nothing beyond 4 meter. And look back to where the A reaction is. This is the A reaction. So your drawing is going to go up if you have a supporting force going up. If this one is not going up, it's going down, then this will start from the negative value. So this is what the shear force diagram is. It is just a constant and two different constant value. And when you go to the 2 meter, it was 2.5 thousand, but because we push down with a 5,000, so it will minus this. So 2.5 will minus 5, that will result into the negative 2.5. So whenever you have a concentrated load to the member, your shear force is going to have a jump. How much jump is depends on how much of this concentrated load that you are making in the diagram. The next one that we will do is to look at the bending moment diagram. So here, you're looking at the bending moment diagram. We're using this equation and this equation to make the drawing. At the first part is 2,500 times x. So that means you have moment proportional to the x. When x is 0, this value is 0. When x is equal to 2, then your moment is going to be equal to 2,500 times 2. That is going to be 5,000, which is a 5K. And this is what this 5K is. So this should be the K here. And it's going to be proportional to that. And slope is going to be 2.5 thousand. Beyond that, you are going to have this equation. This equation is 10,000 minus 2.5 thousand x, which is this one here. That means when x is equal to 2, what is the value? When x is equal to 2, you're going to have 10K minus 2.5K times 2. That is going to be 5K Newton times meter. And that is exactly what this value is. When the x equal to 4, you have, it should be kx, 10k minus 2.5k times 4, and that is going to be equal to 0. And that is what this value is equal to. So these two diagrams is the key point they have to do after you know the 7.1, 7.2, and 0.3 is to ask you to know how to draw these two diagrams. And the most important thing is that what is the maximum value of the shear force? What is the maximum value of the bending moment? Because those are the key number that we need to consider when we design any of the member in the design. Okay, let me go to another example. This example is an example that you have distributed load. How do we draw a bending moment diagram and shear force diagram if we have a distributed load? So we follow the same procedure. We have to find the supporting force first using the entire free body diagram. So this is the entire 3D body diagram. We know we have an AX at AY at here. We have a BY at here. And even though there's an AX, but we know there's nothing else. So this is going to be equal to 0. So we can kind of discard this one. For the entire one, you are going to sum this distributed load to a resultant load at a certain position, the central position. And this is a simple triangle. So we do this one a lot already. So you're going to find a resultant load at 1/3 away from the highest point. So the highest point is the entire length is 9 meters. So 1/3 of that away from the B is going to be 3 meters at here. This will be 6 meters on the other side. And the resultant is going to be equal to 1/2 times the length of the base multiplied with the height. And that is going to be 27,000 Newton times 1,000 Newton. Yeah. So that is the R. Then you can use summation moment and summation force. We have only Y we need to consider, and that will be AY plus BY minus 27,000 equal to 0. We need additional equation. We use the summation moment, and you can choose any position. We're going to choose A position, and let's just assume this is positive direction equal to 0, and A is not create any of the moment. The R is going to create a moment. It's going to be negative because it's clockwise, so it's a negative 27 k Newton times the distance, which is a 6 meters. And we have B, which will be positive. It's counterclockwise. BY multiplied with 9 meters. So then we can find out what the BY is equal to. So the BY will be equal to 18 k Newton. And if this is 18, then you can find AY by plugging this one back to this equation. That's 18. I think this will be 9,000 Newton. All right, so we have these two. And then what we need to do is to go smaller chunk. So now we have this one is 9,000. This at here is 18,000. And then we can go from the left to the right, and whatever the x that you choose, you're going to have a triangle. You have to find the resultant force and find the resultant position, which is this position, right? So this one should be, okay, so for the height of this distributed load, it depends on how much of the x is. You can think about this is going to be 0, and this is the highest point, and we need to find this. So this line here is going to be some kind of slope times the x. But how do you find the slope? The slope is going to be y over x. Your y is this one. Your x is this one. So this slope is going to be 6,000 divided by 9. And that is the slope, which is equal to 2k divided by 3. And that is why we have this one right here. Okay, so if you have a triangle and this height is 2 over 3 k times x, and this part here is going to be the x, because we don't know how far that we will do away from the a, just make it as an x. Then the total amount of the load is going to be 1/2 the base, the height, and that is equal to 1 over 3 kx squared, and that's how this one is coming out. Okay, now we do the same thing. We draw the internal loading. We have a shear force at here. We have a bending moment at here. And we do summation x, summation f, and we do the summation moment. So let's do the summation f of y. Summation f of y equal to 0, and our y has 9,000 going up. We have this much going down. Actually, that should be, let's make this one to be 9. So we kind of ignore the k now. At the end, we're going to multiply with the k. Oops. Back, okay. And we have this v here going down. So it's going to be minus v equal to 0. And then that means the v sub x is equal to 1 over 3 x squared minus 9 k Newton. That's our v. We do summation moment, and we can pick any point. Let's just pick the point of a equal to 0. And we make this direction to be positive. And we will have this resultant force create a moment which is clockwise is going to be negative 1 over 3 x squared k, and it has to multiply with a lever arm, and the lever arm is not x, it's this much, which will be 2 over 3x. And then you're going to add another force, create the moment, which is the v. There will be the sine to be negative v times x. And then you're going to add with m at here, which is positive of m. And n is the one that we try to find. So with this, we can find out n of x is equal to Vx plus these two multiplied together. That will be 2 over 9 x cubed of k. Okay, but what is V? Well, V is this one here. So if you put V into this equation, you have 1 over 3 x cubed minus 9 x squared, 9x, yeah, 9x. And you're going to plus 2 over 9x cubed. And this all in thousand. I should have put 1,000 at the end, so there's no confuse. Okay, so we can sum these two together, right? So this is 1 over 3, 2 over 9 is actually equal to 5 over 9. So this will be equal to 5 over 9x cubed minus 9x, and that'll be k. So that is our moment equation. So what does the bending moment and shear force diagram looks like? So this is our initial structure. If you see this at 9,000 Newton, you're going to start with the 9,000. That's what we showed you before. Any concentrated load is going to move the V, depends on the direction. If it push up, it's going to move up. If it push down, it's going to move down. So you start with a 9,000. Then you're going to follow this equation. So this is going to be the 9. Oh yeah. This sign should be minus here, which means I might need to change this one as well. This is a little bit. This is going to be wrong. But anyway, this one is this one here. So this is your V equation. If you look at the V equation, you will see this is not like a single slope. This is a parabolic line. And the most important part is that what is this value here, and when are you going to have the value go to 0? You can use this equation to find out, well, if you wanted to know where the location is going to be 0, you're going to say, okay, 9 minus x squared divided by 3 equal to 0. I wanted to know what is x, right? So x squared is going to be equal to 27, and x is going to be square root of 27, and that's equal to 3 over 3 times square root of 3, which is equal to 5.2. That is the position you're going to have the 0. After that, it will just continue to go parabolic until you reach to 9 meters, right? So you can find out what is this value. If you put V, that x is equal to 9, and you will find out this is going to be 9 minus 3, 9 squared. And that will be equal to negative 18. And that's why you got negative 18. But it's okay, because at the end, we're going to push it up 18K. So it will move up to the 0 point. And this is what we just said. If you go out, you go beyond the member, there's no shear load on this graph. Well, the bending moment diagram is more complicated. As I said, this one is wrong, so I should fix this one, because the sign of this one is opposite, so I should use positive at here and minus at here. And if I do that, this will be positive, and over here, that should be a negative, it should be 1/9, so this will be 1/9. And you can see this is exactly the same as this one here. So the moment is 9x minus, oh, it should be minus minus x cubed divided by 9. And if you draw this line here, it's going to be this parabolic curve, and you can find where the maximum is, right? How do we find maximum if you know this equation? You take the derivative of this one and make it equal to 0, right? Because at this point, the derivative is the slope, and this point slope is equal to 0. So we take the d of dx of 9x minus x cubed divided by 9, that is equal to 0, and we find out this 9x derivative with dx is equal to 9, and this one here is 1/9 times 3 times x squared equal to 0. So that'll be 3 here. So we have a 9 equal to 1/3 x squared, and x squared is equal to 27, which means x is equal to square root of 27, and that's equal to 3 square root of 3, which is the same as the 5.2. Okay, and what is the maximum value? You put x is equal to 5.2 into that 9x minus x cubed divided by 9, and that will be equal to 31.2. So here, this is what our shear force diagram and bending diagram is coming from. I want to summarize this one with this equation right here. So 9.3 is talking about what is the relationship between shear and moment diagram, and when you have distributed load, what happens? Basically, if you go back to this diagram, you will see the shear force diagram is going to be distributed load integration. So it's calculating the area of this one here. But it starts with some value. When this one pushed down, it will slowly decrease this value. But it doesn't decrease it in a constant value. It decreased as a curve. Where the moment diagram is actually equal to the area of this one here. It is accumulating to sum the area of the shear force diagram. So you will slowly increase, because this is always going to be a positive area. All right, this is the positive area, and you are including more and more of the area, but every time you increase, you are increasing smaller amount, right? So when you are starting at this value, the next step, your increase moment is going to be smaller than your previous step, right? And as long as when you go almost to the top, your increase will be smaller because you are increasing by the smaller amount. When you reach to the peak, what happened? The area become negative, so you start to decrease the moment until you go to the zero again. So beyond, remember your shear force, your bending moment will always equal to zero. And that is how they are related. So here, the 9.3 just tell you when you wanted to find the change of the shear, it is actually looking at what is the area under the loading curve. If you have distributed load, then you will have this value. If you don't have distributed load, such as this one here, if you have distributed load here, and then you have nothing in between, that means your Wx is equal to 0. When you have this one equal to 0, when you do the integration, it's going to be 0. That means there's no change of this value. But you are going to have a change of the V because this distributed load. If your distributed load is a constant like this, that means your Wx is a constant, such as 1000. Then when you do the integration, it is going to have the change of the shear force as a slope. So when you do the shear force diagram, you're going to see this kind of a picture. Oh no, it should be the other way around. It should be going down because it's pushed downwards. Moment is going to be the integration of the shear. So if you have a shear equation, we can actually calculate the moment equation by using an integration, because change of the moment is the area under the shear diagram. So the 7.3 is simply to give you this idea. But if you know how to draw these, you will see, again, the moment diagram is going to be equal to the integration of the shear diagram. And you will see if we put the V 9 minus x squared divided by 3 dx, and what is this integration? This is going to give you 9x minus 9x cubed, which is this one here. And that's how they are related. So when you go from here to here is integration. From here to here is integration. If you go back, it's going to be differentiation. It's a very similar idea like you learn velocity, acceleration, and the position, right? If you see the position diagram, you do integration, you got velocity diagram. You do another integration, you got this acceleration diagram. If you do differentiation, then you got the other way around. So I hope that you understand the chapter 7, and that's the main point for this chapter.